Welcome and thank you for joining me in this lesson. Here we are going to discuss the connection between a scalar and a vector equation of a line. So we're going to take as an example the scalar equation of the form y equals mx plus b, and we'll compare it with a vector equation of the same line, which should be in the form xy equals x0 y0 plus some multiplier t multiplied by the coordinates of the direction vector a comma b. So here we have a line L, and in order to determine the slope of the line L, we can pick any 2 points on the line. And then we measure how we have to move vertically and horizontally, so we travel from points A to B. So to go from A to B, we must run A units, lowercase a units, and we must rise B units, lowercase b units. So we're going to say that the slope is a rise over run, so with a rise b and a run a, the slope will be b over a. So if you want to determine the direction vector of this line L, then we can pick this vector here ab and transfer it with a tail at the origin of the Cartesian plane. That will form the vector OC. So vector OC will define the direction vector for the line L. If you look at the coordinates of point C, then we're going to say that to go from O to C is the same as if going from A to B. So we must run A units horizontally, and we must rise B units vertically. So that tells us that the horizontal coordinate of C will be A, and the vertical coordinate of OC will be B. In other words, we'll say that the direction vector M will be, or will have the coordinates A for X and B for Y. Now, if you compare the slope of the vector when given, of the line, when given in the slope y-intercept form, and the coordinates of the direction form when the line is in vector form, you can tell that there is a connection here. So if the slope is b over a, then the direction vector of that same line can be created by switching these two coordinates. So the denominator will be the x coordinate, and the numerator will be the y coordinate of direction vector. So in the next example, what we are going to do is find an equivalent vector and parametric equations if the line is given in scalar form. So what we are given here is a line in scalar form, y equals 3 over 4 x plus 2. And what we are trying to find in here is both a vector equation, which should be in the form xy equals x0 y0 plus t, and then direction vector ab. And then from here we can derive the parametric equation. So let's get started with the vector equation. So the vector equation will need the coordinates of one point and the direction vector. So the direction vector can be derived from the slope of the given line. So since the slope is equal to 3 over 4, then we're going to say that the direction vector of the same line must be 4, 3. So with this, we're going to say that we have discovered the coordinates of the direction vector. So we have created part of the equation. Remember that x and y will still sit where they were. And now we are missing a point. Now remember that this vector here, or x0, y0, represents the coordinates of a vector that has the head on this line, or the coordinates of a point on a line. So we are going to say that if you want a point on the line, where else can you get it? So we're going to obtain this from the equation that is given in scalar form. How many such points can you find, or how many points can you find that lie on the line y equals 3/4 x plus 2? So if you think about it, there is an infinite number of points you can figure out, or you can find, that lie on this line. And you can find them simply by giving x any value and calculating the corresponding value of y. But there is one point that is ready to use in this equation, and that would be the y-intercept. So the y-intercept is 2. And the y-intercept is a point just like any point on the line. The coordinates of it are 0 and 2. So we'll say that the vector equation of this line is 0, 2 plus t 4, 3. So with this, we've answered the first part of the question. And now we can create the parametric equations. Remember, for parametric equations, we always go the x coordinates and then combine the y coordinates after. So we'll have x equals 0 plus 40, which simplifies to x equals 40, and y equals 2 plus 3t. So the two parametric equations of this line in 2D are x equals 40 and y equals 2 plus 3t. Now we're going to take a look at another example. So in the next example, we have to find the vector equation of a line that is perpendicular to the given line, and it passes through the points 6 and 5. So let's get started. So the information given in this case is some line L with equation 4, 1 plus s negative 3, 2. So what we are trying to find in here is another line, and I'm going to give the lines a name, so lines L1 and L2, such that L2 is perpendicular to L1, so the two lines are perpendicular. We don't know what the equation of this line will be, but we do know that it must be in the form xy equals x0, y0, plus some multiplier t, and then AB. So since the two lines are perpendicular to each other, what we are going to do is use the direction vector of the given line. So we're going to say that the direction vector of the given line has the coordinates negative 3, 2. Therefore, we're going to say that a possible way to write the slope of this line will be m equals, remember that for the slope we have the y on the numerator and the x in the denominator. So this is one way of writing the slope, but it can also be written as negative 2 over 3. So either or should be fine. I'm going to stick with this value. Now, if the slope is 2 over negative 3, of a line is 2 over negative 3, therefore we're going to say that the slope of the perpendicular to it must be equal to negative reciprocal. So negative negative 3 over 2. So the slope of perpendicular is 3 over 2. So knowing the slope of a line, we can derive its corresponding direction vector. So we're going to say that the direction vector for the second line, for M2, will have the x-coordinate equal to the run, so that's 2, and the y-coordinate equal to the rise, so that's 3. So with this, we have discovered the direction vector for line L2, and again, this is a possible direction vector because any multiple of it will do the job just fine. And we'll say that so far we have the equation in the form xy equals, so some starting vector plus t following the direction of the vector 2, 3. Now we have to think of how to figure out what point to put in here. Now remember, if you are given a line L1, and I'm going to draw one right here, we're going to say that we can draw many perpendiculars on this line. So if you are asked for any perpendicular, then you can very easily use this point. But in this case, we're asked to find a perpendicular that passes through 6, 5, which means that the direction vector R0 for the second line would be equal to the vector OP, which is 6, 5. So 6, 5 is what goes in for x0, y0. So we'll say that the vector equation of a line perpendicular to the given one will be xy equals 6, 5 plus t 2, 3. So this is it, and I hope that this made sense. Thank you for watching.